It is possible to have an aerodynamic or hydrodynamic vehicle maneuver without using movable control surfaces. This is by using impulse jets. This is similar to how rockets or satellites maneuver or stabilize in space. Small jets of propellant are emitted to provide forces to stabilize or control the vehicle. The point of this system is that the space vehicles tend to use liquids, which are very volatile and very hazardous and very difficult to handle. The idea of this is to use small amounts of solid propellant to achieve the same effect. The system would be mounted inside the fins of rockets or torpedoes, and they would fire upwards through the edges of the fins. In supersonic speeds, a wedge or triangular shaped fin is actually pretty efficient and provides a good flat top surface for the installation of the small jets. The amount of propellant needed really isn't that large for small maneuvers. If you allow for 67 pounds per square foot for the wings, which is the loading level of an F-15 or an F-16, at supersonic flight, if you say 4 Gs, wings are less efficient at supersonic flight than at subsonic flight, you get about 300. If you have 4 1 square foot wings, or winglets, or fins, they are rotated at 45 degrees. So they have an effective area of 2.8. It's 4 times 0.7. 0.7 is the cosine of 45 degrees. They're rotated at 45 degrees because if you have them flat, you only have 2 square feet. And rotated at 45 degrees, you get 2.8 square feet of effective area, which gives you some more lift for maneuvering. If you multiply 300 pounds per square foot times 2.8, you get 800. If you allow for inefficiencies and say, well, you need 5,000. If you're allowing 5,000 pounds of force being necessary, and if you want the planes to displace by 1 foot, so a typical air-to-air missile is about 10 feet long, the distance from the center of mass to the fins is going to be 5 feet, so 1 foot of displacement would be about 12-degree deviation in angle. So 1 foot difference in displacement would be about 12 degrees of course correction. If you have 5,000 pounds times 1 foot, that's 5,000 pound-feet. High explosives, which have similar energy values to propellants used in rifles and artillery shells and such not, have an energy value of 1.5 million pound-feet per pound of explosive. So you need about 1/300th of a pound. That would be about 1.5 grams. A pound of explosive weighs about 100 pounds per cubic foot. That's 1/30,000th of a cubic foot. It goes about 1/30th of a foot in each direction if it was a cube. That's about 1 centimeter. It would probably be better to have a smaller amount of propellant to have a finer angle of adjustment than 12 degrees. It's quantized. Every time you fire the propellant, it's going to move a fixed amount because they're solid propellants. And so the amount of energy they give cannot be adjusted. And then the question becomes, how many times do you want it to maneuver? How many little pulses do you need? So what you have is a vertical column of them with little pockets off to the side where there's the propellant. Then in front of the propellant, there could be a block of plastic. And the idea of the plastic is so that when one charge fires, it doesn't ignite all the other charges. And the question is, how much would they ablate? How much, when you fire one, would it cause erosion in the other protective pieces of plastic? And then you'd have an electrical firing system to make the whole thing work. This can also be used in torpedoes, and it can be used in artillery shells. The modern maneuvering artillery shells are very expensive to make. They have little winglets that actually fold out to give them some aerodynamic control. You can make an artillery shell that is smaller in diameter and has fixed winglets. And then you have some kind of sabots on the outside to fill up the rest of the barrel. If you're firing it out of a smoothbore artillery piece, this works best. It will have a smaller explosive charge than a conventional shell, but you can have those fixed winglets. And again, the fixed winglets can have these little propellant control devices. And that can make the shell much less expensive to produce. The shells will probably also have a shorter range, but take the bad with the good.